Imagine accidentally brushing your bare hand against a searing hot stove. Before you even realize what has happened, your arm jerks back. You pull away from the danger before your brain actually consciously registers the pain. This lightning-fast reaction relies entirely on your nervous system, a specialized biological network dedicated exclusively to high-speed communication. Every time you interact with the outside world, your safety and survival depend completely on how efficiently this internal network can send a message. Looking at this anatomical diagram, you can see the sheer scale of that network. From the thick bundle of the central spinal column, a dense web of nerve branches reaches out to the very tips of your fingers and toes. This sprawling highway isn't a single continuous wire. It is built from millions of individual microscopic nerve cells called neurons. Because these are microscopic units, passing a message across the body is a massive physical challenge. These tiny cells have to successfully hand off a single warning signal across vast relative distances. If this cell-to-cell relay fails or slows down for even a fraction of a second, severe physical injury is guaranteed. Down at the microscopic level on this slide, you can see the biological structure of a single neuron, with sprawling extensions radiating from its dark central nucleus. At the extreme edges, specialized receptor tips act as environmental sensors, waiting to detect changes like intense heat. This highly specific receiving area of the cell is known as the dendrite. When intense heat touches the skin, that sensory input sets off a sudden, highly localized chemical reaction right at the tip of this dendrite. That precise chemical reaction is the critical moment your body successfully translates a physical danger into a biological signal it can actually read. This initial chemical trigger immediately sparks a sudden electrical impulse. The signal surges inward, passing directly through the main body of the cell. It then enters the axon, a long cable-like structure, and races toward the very end of the cell. Compared to the initial chemical reaction that started it, this electrical transmission phase operates at extreme, blinding speeds. Electricity is the fastest possible way to move information, making it the body's chosen medium for ensuring these long-distance signals arrive almost instantly. But at the end of the axon, the signal hits a roadblock. There is an empty physical gap separating this sending neuron from the next receiving cell. This microscopic void is called a synapse, and an electrical impulse physically cannot jump across it. Hitting this dead end forces the electrical signal to adapt. It triggers the axon to release a batch of specific chemical messengers. These chemicals act as ferries. They drift rapidly across the fluid-filled gap and lock securely into specific receptor slots on the opposing wall. Once those chemical messengers dock tightly into the dendrite of the next cell, they spark a brand new electrical impulse, continuing the relay. Your nervous system is essentially bilingual. It constantly translates between rapid electrical pulses and chemical bridges to keep the message moving without a single interruption. Eventually, this chain of firing neurons reaches its absolute final stop. This last connection point is called the neuromuscular junction. It is a unique synapse where the nerve cell connects directly to muscle tissue instead of another neuron. Here, the final release of chemical messengers flows across the gap and commands the muscle cells to instantly change their shape and contract. That invisible microscopic release of chemicals is the actual mechanical force that violently pulls your hand away from the flame. When you step back and look at a person reacting to a hot stove, the seamless nature of the movement hides the incredible complexity underneath. This entire translation from a localized chemical trigger into electricity, across countless synapses, and finally into contracting muscle, happens in a fraction of a single second. This precise anatomical design is the silent engine driving all animal survival, allowing us to navigate, react, and exist safely in the physical world.